All right, so suppose one bag of M&Ms is sorted and counted by color, and it's determined that there are 55 total M&Ms in the bag. I could describe how many as a list. I could just describe how many M&Ms are in each bag, but more valuable is to set up a table that shows that information. So I could set up a table that sorts color and identifies the frequency or the count for each color. So the colors I have are brown, red, yellow, green, blue, and orange. And in this one bag, I found 17 brown, 18 red, 7 each of yellow and green, 2 blue, and 4 orange M&Ms. So in this form, and I could list that I have the total is 55 total. So this represents a frequency table or a frequency distribution, meaning that the M&Ms in the bag are distributed by color in this in these numbers or these amounts. So this would be a frequency table because it's a table, or frequency distribution. For these M&Ms. Tables are useful. It's easy to see how many of each M&M, but comparatively speaking, tables aren't usually very useful for determining or understanding a set of data. So in that case, we want to work with a graph of some sort. And in this situation, I think the best graph is probably a bar graph. So I'm going to identify the frequency as some value or some height of a bar. So there could be 0 of any given color in any given bag of M&Ms to 5, 10, 15, 20, and because 17 and 18 are pretty big numbers, it's possible to get a bag with just over 20. I'm going to say 25. Anything that had more than that would likely be an outlier, but of course I'm jumping the gun here. At this stage of the game, I don't really know how many M&Ms are in each bag by color, and so I'm just going to spread the data as far as I can to make it easier to see. And then let's identify by color. So we have brown, red, yellow, green, blue, and orange. And then all I have to do is determine what height bar would represent the number for each color. So if this is brown, has 17, that would be just slightly over 15. And then red has 18, so that's going to show as a bar slightly higher than the 17 for brown. And then yellow and green both have 7, which I think is probably right about there. Of course, you can be more exact if you need to by having, graphing utility or graphing paper. And then blue has 2, so that would be a small value. And orange is 4, about twice the height of blue, but less than 5. All right, so that would be a distribution table. A distribution graph that describes the frequency in the bag of M&Ms by color. So a bar table like this, from a table like this, is a great way to describe the distribution of a discrete variable. So that's one sort of distribution that you may work with. Discrete meaning if you open a bag of M&Ms, there is going to be one value for each color. You can't have 17 brown M&Ms and 6 brown M&Ms in the same bag. That would be crazy. You only get one discrete value for each color. So another more useful way to deal with the same or to display the same information might be with a probability distribution. So we'll look at a probability distribution, also constructed as a bar graph. But instead of looking at the raw numbers, because this isn't so useful unless you can predict the value or the number of M&Ms of any given color in any given bag. And because this is a bag with 55 total M&Ms, unless you get another bag with 55 M&Ms, you don't really have a lot of foundation to predict the number of brown M&Ms in that next bag. But if I know the percentage of brown, then I can just maybe extrapolate how many M&Ms I think are in another bag by percentage. So in that case, we want to set up a table slightly different. I'm going to keep the same values for color on the bottom. The same. I'm going to sort on the x-axis by color. But on the y-axis, instead of frequency, I'm going to evaluate the proportion. Meaning the percentage. And the proportion would be the number by color, in this case divided by the 55 total. And my range will be somewhere in the category of 0, 0.1, 0.2, 0.3, and let's go with 0.4. I think it's unlikely 17 is not nearly half of 55. I think it's unlikely that we'll go that high, so that looks like a good range for my proportion graph. And then the values I get for my proportions, rounded to the nearest hundredths, are 31% brown, 33% red, yellow and green are each 13%. Blue is 4%. And orange is 10%. So now this information is much more useful. I've drawn it in a way that it's not so easy to see. Let me see if I can scooch this over a little bit. There we go. So the proportion distribution is so much more useful because suppose I buy a bag of M&Ms that has 500 M&Ms in it, and I need to know how many I'm going to have of one particular color. Well, 500 multiplied by the percentage, so 500 times 31%, 0.31, equals, let me get out my little calculator here. $155. So I would expect to find 155 M&Ms that are brown in a larger bag of M&Ms. So all three of these, the table and two graphs, are excellent ways to describe the distributions of discrete variables. Let's look now at distributions of continuous variables. So an experiment is set up where one person running 20 trials meaning 20 times, is asked to move a cursor over a particular marker on a computer screen, and the time it takes to do so is measured in milliseconds. So this is time in milliseconds. So when you think about this, the odds, especially when we're talking milliseconds, the odds of one person hitting even the same exact time in milliseconds to carry out the task twice is so exceedingly unlikely that this is a terrible variable to evaluate as though it were discrete. And so we're going to look at it instead as a continuous variable. We're going to look on a range. So first, let's record our data. So response times. And we know that there are 20 of them. So let's see, I think I have room for 2 columns. So the various response times for the one person over 20 trials is 568 milliseconds. Let's write in milliseconds, not milliseconds. 568, 577, 581, 640, 641, 645, 657, 673, 696, and 703. So that's the first 10. And then the second 10, 720, 728, 729, 777, 808, 824, 825, 865, 875, and 1007. All right, so at this point, the only way that the data has been packaged is it's been written in descending order or ascending order from the shortest to the longest response times. So clearly, if I were to set up a bar graph for frequencies on this table, I would just have, on the x-axis, I would have 20 entries and they would all have a frequency of exactly 1. So this does us no good at all evaluating as a discrete variable. But as a continuous variable, we can determine a range. So we can take this information and decide on a range. For each value. So if I were to say in another table, I have a range is 500 to 600, 600 to 700, 7 to 800, 8 to 9, 9 to 10, and 1000 to 1100 or 1100. So now it's very easy to sort this data. If I start to count, how many of these values fall between 500 and 600? Well, that would be these 3. How many from 600 to 700? 1, 2, 3, 4, 5, 6. 700 to 800, 1, 2, 3, 4, 5. 8 to 9 is 1, 2, 3, 4, 5. 9 to 1000, this is 0, and then 1 between 1000 and 1100. This is called a grouped frequency distribution. And the table we're going to form or create looks quite a lot like a bar graph, but it is not. It is actually a histogram. So let's set it up. Starts looking like a bar graph. And our values are easy to spread. 0, 1, 2, 3, 4. That's not a good good spread. 0, 2, 4, 6, 8. We could write 10. All right. And then across the bottom, what we want to do is we want to allow for each of these spreads. So the 500 to 600 is going to be this first group. I'm going to label it right at the center of that data. And then the next one, same size, same width, because it covers the same amount of data, but I'm going to label it also right in the center of the data. The next one is 750, probably over here a little more, 850, 950, yikes, running out of room. Let's see, I know, you guys hate when I do this. You're going to hate it because you can't do this on your paper, but I want to get this video over with and get you on your way. So we're going to call this one then 1050. Okay, so just like a bar graph, we're going to rise this whole area to this range. So there are 3 occurrences in this range. And then the next range has 6 occurrences. And notice how the graph fills in. So the bar graph, I had spaces between to identify discrete colors, but in this case it's continuous, so the whole thing has to sort of continue on. Then for 750, this range, I have 5. 850, in this range I have 5 again. 950, I have 0, and then the last range I have 1. And then when I color it in, you can see that this covers all the data, and each of these bars, let me change the color on one just to talk about it. This bar section represents 6 different data points in this interval. And so this is a histogram, which is a much more efficient way to describe a data distribution on a continuous variable. All right,